So today we'll be looking into the electrophilic substitution reactions of benzene. So firstly, an electrophilic substitution reaction is where you form two products from two reactants. So as the name suggests, this reaction mechanism actually involves an electrophile, and an electrophile is anything that seeks for negative centers and it is positively charged. So this moves us on to our first reaction that we are going to be looking into, and this is called the nitration of benzene. In this reaction, we take our benzene ring and it undergoes a reaction with concentrated nitric acid, so HNO3, in its aqueous state, and we form nitrobenzene. So nitrobenzene, so we're going to have NO2 over here, and we form water. So now the reagents and conditions for this reaction is, well, we require a catalyst, and a catalyst in this reaction is going to be the concentrated sulfuric acid, so H2SO4, and the temperature we need to maintain is 50 degrees Celsius. Now, if the temperature is above 50 degrees Celsius, that means we will form, let's say, dinitrobenzene or trinitrobenzene, so it would undergo more than one substitution reaction. The nitration of benzene and this reaction right over here is actually composed of three steps. So firstly, the nitric acid is not our electrophile, therefore we need to generate our electrophile. So step one would be the generation of the electrophile. So to generate our electrophile, we are going to take our nitric acid, so HNO3, and it will react with the sulfuric acid, our catalyst. Concentrated sulfuric acid and concentrated nitric acid will undergo a reaction, so H2SO4, and this would form NO2 plus HSO4 minus, and a water molecule. So now when we are identifying our electrophile over here, well, our electrophile would be this ion right over here, and this is actually called a nitronium ion, and this would be our electrophile for this reaction. So if we just move on to step two, and so step two would be our substitution reaction. So if I just write it down over here, step two, substitution. So it is a substitution reaction, and therefore it would involve some curly arrows. So if we take our nitronium ion over here, NO2 plus, and so we know this ring, this delocalized ring of 6 electrons, it's representing, well, it's representing 6 electrons, and it's electron rich. And our NO2 plus, which is electron poor, it doesn't have that many electrons, it needs to gain electrons. Therefore this ring will donate 2 electrons to the nitronium ion. So it would donate 2 electrons to the nitronium ion, and that means the ring would be disrupted. So we represent the disrupted ring by drawing this horseshoe shape, and this horseshoe shape needs to represent 5 carbons. So if I just make the nitronium ion, well, the nitronium ion forms a dative covalent bond over here. So, and don't forget that we actually have a hydrogen over here as well. So for this step, we actually need to draw the hydrogen out, and we know that this is disrupted and it has lost electrons. Therefore, this intermediate will gain a positive charge. So now this is in a very unstable state. Therefore, the carbon to hydrogen bond will donate an electron to the disrupted ring, and this would reform our benzene ring, and our will form nitrobenzene, so our NO2, so it would form nitrobenzene, and well, this bond right over here has donated electrons, therefore we would form a H plus ion. Now we move on to our step 3. So we have formed our nitrobenzene, however we still need to regenerate our catalyst. Therefore our step 3 would be the regeneration of the catalyst. So regeneration of catalyst. So to regenerate our catalyst, we need to pay attention to the products of step 1 and step 2. So in step 1 we produced a SO4 minus ion, and in step 2 we produce a H plus ion. So these two would react together and they would form a sulfuric acid. So H2SO4. And now our catalyst is regenerated. Okay, so now this moves us on to our next reaction, which would be called the halogenation of benzene. So halogenation of benzene, I'll just write halogenation. So in this reaction, we'll take our benzene ring and we'll react to with any halogen. So let's say in this example, we have bromine, so Br2, and hence we'll form bromobenzene, so Br over here, and we'll form HBr. Now, the reagents and conditions for this reaction are that we again require a catalyst, and well, a catalyst over here is phrased. There's a fancy phrase for our catalyst, and it's actually called a halogen carrier. So our halogen carrier would be FeBr3 for this example, and the condition would be room temperature and pressure. So now again, focusing on the catalyst, this could have been I mean, because we are using bromine, we are using FeBr3. Well, if it was chlorine, it was going to be FeCl3, or if it was iodine, it was going to be FeI3. However, instead of iron, you can also use aluminium, so we can also use the halogen carrier AlBr3. However, both of them are acceptable. So now, because our benzene ring is so unreactive, therefore our bromine molecule will require a halogen carrier. So now we move on to our step 1, which would be the generation of the catalyst. So step 1. Now, to generate the catalyst, we'll take our bromine molecule and it would undergo a reaction with our halogen carrier. So Br2 plus FeBr3, and we'll form our Br plus ion plus FeBr4 minus ion. Now, in this case, our Br plus, which is actually called the bromonium ion, is going to be our electrophile. So now we are going to use this electrophile in our next step, which is step 2. And in this step, this is actually called the substitution step. So step 2. And in this step, we'll take our electrophile, which is the bromonium ion. And as I mentioned earlier, this ring represents 6 delocalized electrons, and it's going to donate 2 of its electrons to the bromonium ion, and therefore the bromonium ion is going to form a dative covalent bond with the benzene ring. However, it does disrupt the benzene ring, therefore we do have to make this horseshoe shape, and it has to cover 5 carbons, and this intermediate would have a plus charge because it has lost electrons. And don't forget to really draw out the hydrogen over here, because the hydrogen to carbon bond would donate its electrons to this intermediate, so that the delocalized ring can reform, and now we have a bromobenzene plus our H plus ion. And this moves us on to our third and final step, which is going to be the catalyst regeneration. So step 3. Now, to regenerate the catalyst, again, our step 1, the product of step 1, which would be FeBr4 minus, and we are going to add our H plus ion, and we are going to form FeBr3, our halogen carrier, which was just a fancy word for saying catalyst, and we are going to also form HBr, and that would be it. So now we look at the third reaction that benzene undergoes, and this reaction is actually called the alkylation of benzene, or it's actually sometimes referred to as a Friedel-Crafts alkylation. Friedel-Crafts alkylation. Now, over here we'll take a benzene ring, and it would actually react with a haloalkane. So let's say we have 2 carbons, Cl, hydrogen over here, so it would react with chloroethane, and we are going to form ethyl benzene, so C2H5 plus HCl. Now, the reagents and conditions for this reaction is that again we'll require a halogen carrier. So this time the halogen carrier would be AlCl3, and the condition would be room temperature and pressure. Moving on to step 1, which is our electrophile generation. So step 1, and in step 1 we'll take our haloalkane. So in this case it's chloroethane, so C2H5Cl, and our halogen carrier, so AlCl3 in this case, and this will undergo a reaction to form C2H5 plus AlCl4 minus. Now the electrophile in this case is going to be C2H5 plus. Now this electrophile is going to be used in step 2. So step 2, which is going to be our substitution step. So step 2. Now our electrophile C2H5 plus going to be right here, and so the delocalized ring, which represents 6 electrons, will donate a pair of electron to our electrophile, and we have to show that by making the curly arrow. And again, so this will cause the ring to have a disrupted shape, and this shape should cover 5 carbons, and it would have a positive charge. And now the C2H5 plus ion would form a dative covalent bond with the bromine molecule, so C2H5 plus, and don't forget to again draw the hydrogen, because we have to, because hydrogen and carbon to bond, a hydrogen to carbon bond donates electrons to this disrupted ring to reform the delocalized ring over here, and we form ethyl benzene, so C2H5 and a H plus ion. So now we move on to our third and final step, which would be the catalyst regeneration. So step 3 will take our products of step 1 and step 2. So AlCl4 minus, so AlCl4 minus plus H plus, and we'll form our halogen carrier AlCl3 plus HCl. Now we'll be looking into the fourth reaction benzene undergoes, and this is actually called the acylation of benzene, and is sometimes referred to as the Friedel-Crafts acylation. So now over here we'll have a benzene ring, and it will undergo a reaction with the ethanoyl chloride. So if you have C double bond O, C3H, CH3, and Cl. So if you can see this functional group right over here, this functional group right over here is called acyl chloride. And so benzene reacts with the ethanoyl chloride, and it would form phenyl ethanol. So we have a ketone over here with 2 carbons, therefore it's phenyl ethanol, and HCl, so we'll form HCl as well. So now the reagents and conditions for this is that we actually again require a halogen carrier, and this time it's going to be AlCl3, and the conditions are room temperature and pressure. Okay, so step number 1, electrophile generation. So we'll take our ethanoyl chloride, so C double bond O, CH3, and a Cl over here, and we'll add our halogen carrier, so AlCl3, and now these would undergo a reaction to form C double bond O, CH3 plus, and AlCl4 minus. Now our electrophile over here is this, so let's write over here electrophile, and this would be used in step 2. So our step 2 is the substitution reaction. So step 2, substitution. Now over here we'll take our electrophile, which is the C double bond O, C3H, and our delocalized ring, which represents 6 electrons, will donate a pair of electrons to our electrophile. So there's a plus charge over here as well, and now this electrophile will form a dative covalent bond with our benzene ring, so C double bond O, CH3, and it would disrupt the structure of the ring. So now the ring is disrupted, and it's represented by a horseshoe shape, which again needs to cover 5 carbons, and it has a plus charge. Now again we have to draw the hydrogen over here, and the carbon to hydrogen bond donates electrons to the disrupted ring because it's very unstable. Now the ring reforms and we form our phenylethanol. So phenylethanol, CH3 and our H plus ion. Now this moves us on to our step 3, which is the regeneration of our catalyst. So step 3 would be right over here, step 3. Now again, our products of step 2 and step 1, which is AlCl4 minus, it's AlCl4 minus plus H plus, and we'll form our halogen carrier AlCl3 and HCl.